Scientists! Today we're going to talk about forces. To get started, let's make a copy of our notes. You can go to the Module 4 Topics page and make a copy of the template there, or ask for a paper copy of the notes. Your proctor might have one. Please pause the video and make sure that you're all set up to take notes. For notes today, you'll see that there are some spaces where you have the sentence starter and you need to write it in, and then there are some spots where I'm going to go into a little more detail and you don't need to take notes. I'll try to make it obvious as I go through. So by definition, a force is a push or pull on an object that is resulting from that object's interaction with something else. So for example, here we have the soccer ball, and there's going to be a force applied to that soccer ball when Megan Rapinoe kicks in. So her kicking the ball, right, her interaction with the soccer ball, is going to create a force that acts on that soccer ball. We measure forces in newtons, which is symbolized as a capital N. The newton is the amount of force it takes to accelerate 1 kilogram of a mass at 1 meter per second squared. But we just take that unit, kilogram, meter per second squared, and it's too challenging to write. We just call it a newton and write N. And then one important thing is that force has both magnitude and direction. So we'll have an amount of force measured in newtons, and then we'll have the direction that that force is being applied. So this kick on the soccer ball looks like it's going to be in the forward direction or towards the right. If you need to pause to finish writing this down, please do so, and then we'll pick back up. I'd like to spend a little time today talking about types of forces. You don't need to write down what's on these beige background slides. At the end, we'll pause. You have a spot to write examples in your notes, and I have a list of them at the end, and we'll pause, and you can write down a few. We're going to talk more about the equation for force later on in this lesson. We'll probably get to it at the end of the week. But for now, you should know that force is mass times acceleration. So the amount of force on something is proportional to how much or takes to move something is proportional to its mass and its acceleration, right? The change of velocity. Now let's get into some examples. So first we have the friction force, and we symbolize this as F sub Fr. And we draw it. You'll see that there's lots of arrows on here. Here we've got a guy pushing a box, and the push direction, you can see the arrow showing that push, and then the friction force acts opposite. You can see it down on the bottom, right, this arrow here. It's opposite the movement, and that force acts against the push and slows down the acceleration. And we always draw the friction force parallel to the surface. Next up, we have the normal force. This one is a little weird, but when we have an object on something, like this book on a table, the pull of gravity, which we'll talk about in a second, pulls it down, but then there's also a force of the table pushing up on the book, right, holding it there, right, supporting its weight. When we draw the arrow for the normal force, we're always going to draw it perpendicular to the surface. So if we had a diagonal surface, we would draw the normal force perpendicular to that. We'll see an example of that later. Then we have tension forces. So this is a force that is transmitted through a string, a rope, or a wire. So we've got two people pulling on a rope here, and they feel the tension force of that wire. And this tension force is equal on both objects that are pulling on it, and we would draw the arrows to show tension force alongside the wire. Next up, we've got air resistance force. This is sometimes called drag. This is very similar to friction, but it's the friction that is on an object from the air molecules. And like with friction, if we're going to draw a drag force, we draw that force as being opposite. Here you've got the little stick figure running, right? It's running in the forward to the right, and the drag force is pushing back towards the left. And we've got applied force, and this is when we apply a force, right? This is often a push force, right? Something that we're doing to exert a force on an object. This also works to describe things like motors, that propel things forward. Then we've got gravitational force or weight, and so this is the force from the Earth, Moon, or other objects pulling objects towards itself. So the acceleration here is the acceleration due to gravity. The Earth is pulling things toward it at negative 9.8 meters per second squared, and the direction is always straight down, even if we have a slant or a slope. And this force is always present, so it's always acting on whatever object we're talking about. So in summary, we have things that we call contact forces, like friction, normal force, tension, air resistance, or applied force, that's like a push. And then we've got forces that are action at a distance. For now, let's just think about gravity. We also have magnetic and electrical forces. More on those later in the year. If you haven't written down any examples in your notes, this is a good time to jot them down. So pause the video, write a few example forces down, and then pick back up. You noticed in all the diagrams in the previous slides that we were drawing in arrows to show how much force there is on an object. And these are called free body diagrams. The definition of a free body diagram is that it's a diagram used to show the relative magnitude and direction of all the forces acting on an object in a given situation. So as a person is pushing blocks, as someone is running down a road, we would take that snapshot moment in time, almost like a photograph, and we would draw in the forces. The length of the arrows is going to show us how much force there is, the magnitude, and then where that arrow is pointing is going to show us the direction that that force is acting. You can take a minute to pause the video here and write down this definition in your notes diagram if you need it. Next up, I have a video for you to watch. I am not going to play this video in the screen recorder, so you can find the link to watch it on your own and then come on back. Here I've got an example of a free body diagram. This is just a box on a table, and we can see a few forces in motion. We've got the force of gravity pulling down. We've got the normal force, the table pushing back up on the box. We have the force of friction that is creating resistance to motion, and then we have this applied force that is extending towards the right. And here the normal force and the force of gravity are the same magnitude, right? The length of the arrow is the same, and so the box isn't going to have any direction in the up or down direction. But my acceleration or applied force to the right is a greater arrow, a bigger arrow than my friction force. And so when I see that bigger arrow, I know that the applied force is of a greater magnitude, and the result is that this box is going to move towards the right. So in general, wherever your longest arrow is, the object is going to move in that direction. And then if you have balanced arrows, we'll see no motion. Last example, I've got this skier going down a hill. I wanted to show you one that was on a slant. And so the normal force you can see is perpendicular to the surface of the ski slope. That's the force of the slope pushing back on our skier. I've got friction and drag that's parallel to the surface of the slope. The friction of the skis on the snow, and then the air resistance, the drag. And then finally, I have gravity pulling straight down, right? That arrow is perpendicular to the bottom of my screen. And you can see the force of gravity, in this case, is greater than the normal force and the friction and the drag. And so the result is that my skier is going to go downhill. He's not going to go straight down into the earth, though, because that normal force is acting on it. So the resulting force is that he'll end up skiing down the slope. All right, so now it's your turn. You are going to check out the 4.3 free body diagram practice, where you'll have a few different scenarios and you'll need to draw in the arrows for the forces. Do the best you can. I don't think you have numbers for any of them, so you can just draw the relative length of the arrows, right? Make them the same if there's going to be no acceleration, or make one longer than the other if there is going to be acceleration. Yeah, do the best you can, and we can check in about it a little bit later in the week. Good luck!